All right, so this homework assignment right here is chapter 16, rigid body kinematics. So the first problem, it gives us this structure right here, and it wants us to find the acceleration of the rod and the reactions at A and B. So right here I just drew like a quick free body diagram of the rod, and when it's equal to this right here, again, this is like from the previous chapter, so the sum of forces will equal mass times acceleration. And that's what we did right here. And then the sum of forces in the x direction, we got P equals to ma, and this helps us get our acceleration. And then part B, we get the sum of moments at point B. And we're doing this right here to help us get the reaction at A. So yeah, we do that for both sides again, and it gives us we plug in what we do know, and it gives us our reaction at A. And then to get the reaction at B, we just do the sum of moments in the y direction, which will equal to 0. And yes, pretty simple right here. We know what A is, we know what the weight is, mass times gravity, and then we just figure out what B is, and that's our reaction at B. So that was problem 1. Problem 2 gives us this system right here, and what it's asking us is the acceleration of the weldment and the reactions at A and B. So again, kind of similar to the previous one, except for this one, we're trying to get we saw for the normal acceleration and tan acceleration. So we use velocity squared over 3 to help us find the normal acceleration. Again, we do a free body diagram, and it's equal to this right here is mass times acceleration. So for the tan direction, we get the sum of forces and the 60 degrees direction. This is what we get right here, and our tan acceleration will be equal to this right here. And then this, we consider the tan and normal acceleration of the weldment. So this is what this free body diagram is right here. We know we don't know. We're trying to figure out the angle right here in between the tan acceleration and the normal acceleration, which gives us this. And to find the acceleration is the square root of tan acceleration squared plus normal acceleration squared, and that's what we get. Now for part B, to find the reactions, we do the same thing as before. It's just this one that's equal to m mass times acceleration, and this is a different free body diagram than before. And yeah, we just take the sum of forces at the sum of moments at A. This will help us get the reaction at B, since this reaction going through A cancels out, since we're getting the moments through here. So yeah, we do the weight times 6, B times 9 is equal to mass times acceleration and the cosine direction and the sine direction, and that's what we get right here. And then we get the sum of forces in the x direction, and then that's what we end up getting for the A reaction. All right, problem 3 gives us these two discs, and it wants us to find the angular acceleration of each disc and the final angular velocity of each disc. So again, like before, this right here is disc A. We do the free body diagram, and then it would equal times the moment of inertia, and the moment of inertia times the angular acceleration. And yes, so here I just solve for the moment of inertia, which is 1/2 times A times radius squared. That's what we end up getting. Get the sum of forces in the x direction, and then it's equal to 0, and we know the n will equal to P. These two, the only two forces going in the x direction. And to find the force, we do the static friction times the natural force, which gives us 3. And now we get the sum of moments at A equal to the moment of inertia times the angular acceleration. So yeah, so we're taking it at point A. So we're only, these two cancel out since they're going through the point. So we only use the force with times the radius and equal to the moment of inertia times the angular acceleration, and we get the angular acceleration to be 12.5. Now this other one, we use disk B, and again, similar to up here. The only difference is there's different radius, and then the only force acting on it is the natural force, and then the force at point B. Again, get the moment of inertia, sum of forces at point B, and this will help us get the angular acceleration at point B, which is 33.3 rats per second squared. And now right here, we're trying to figure out the angular velocity. Again, we use this, it gives us the initial angular velocity at point A. So we use this equation right here to figure out the time. And then we got the time right here. Plug that in to get the angular velocity of A, which is the initial angular velocity minus angular acceleration times time. And this is what we end up getting, 240 RPM. And then for point B, the angular velocity is the angular acceleration times t, times the time. And we saw this in the previous problem, 33.3 times our time. We get it right here, convert it to RPM, and we get 320. Now for problem problem 4, we get this term right here, and it wants us to determine the combined radius of gyration of the disc and drum. So again, draw up the free body diagram. It's equal to mass times acceleration with the moment inertia times the angular acceleration. So yeah, get the sum of forces in the y direction, which is equal to mass times acceleration. And then this will help us get the acceleration, which is 2.19. And now we know acceleration is equal to radius times angular acceleration. And this will help us get the angular acceleration, which is 10.95. And now we have our moment of inertia, which will equal to m times the gyration, the radius of gyration squared, which equals, we know what the mass is, but we don't know. This is what we're solving for right here. So that's what we're ending with. Then we get the sum of forces in the g direction. So this is what we get, which would be equal to the moment inertia times the angular acceleration. So yeah, so we got this. We got a moment inertia, we got the angular acceleration. We know that, and then we just solve for the k, and then we got 171. All right. Yeah. So sorry, I don't sure if I specified, but this right here is what this is equal to this. So yeah, I forgot to put in right here. It's equal to. That's what, if there's any confusion, that's what this is right here. The 1.6 is what this is. All right, and then for problem 5, we're given this slender rod, and it wants us to find the angular acceleration of the rod and the components of the reaction at C. So again, draw up the free body diagram of all the reactions, and we're equal to mass times acceleration, and then we have our moment of inertia times the angular acceleration. The equations for the ones I just mentioned. So we get the sum of forces in the C, point C, which the only reaction that's not going through it is P, and this is the distance from here to here, which equals to mass times acceleration. The radius is the from point G to point C, plus this right here, we got the moment of inertia times the angular acceleration. We plug in the values so that we do know, which we know all of them except the angular acceleration, which is what we're solving for, and it's what we end up getting. Now to find the components of the reaction at C, Take the sum of forces in the y direction equal to 0. Principle right here is just basically what the weight is, which is 39.24. Then we got the sum of forces in the x direction, which would be equal to minus mass times acceleration. So this way you get right here, plug in the values we do know, and we get the c reaction in the x direction to be negative 21.43. In problem 6, this right here was pretty simple. We got a wheel, and it just wants us to derive an expression for the acceleration of the center of the wheel in terms of radius, the radius of gyration, the angle, and g. So basically what we've been doing for each problem, we get the free body diagram, and it's equal to mass times acceleration, and also the moment of inertia times the angular acceleration. Right here is the equation for this, for each one. Get the sum of forces in the c direction, which is this right here. And then basically what we're just doing now is just plugging in these values into here, and then just simplifying it, and this is what we get for angular acceleration. Now we do know that our angular acceleration is equal to well, we know our acceleration is equal to radius times our angular acceleration. Plug in our angular acceleration times the r. The only difference here is just this is r squared, and this is our final answer. This is our expression for the acceleration. Now for problem 7, we're given a drum right here, and it wants us to determine whether or not the disc glides, and the angular acceleration of the disc, and the acceleration of g. So again, free body diagram. I almost forgot to include this, but here I just drew it really small, and which is equal to mass times acceleration times the moment inertia times the angular acceleration. Right here is simplify the moment of inertia and our acceleration. Take the sum of forces in the c direction, which would be equal to the mass acceleration r plus inertia times the angular acceleration. Yep, and then we plug in the values, and we know all the values except the angular acceleration, which is what we solve for right here. Plug that in to get our acceleration. And now we get the sum of forces in the x direction, which will equal to mass times acceleration. And right here we solve for our force, which is this right here. Now we get the sum of forces in the y direction, which will equal to 0. We get our natural force. Now with our natural force, we'll do our kinetic friction times the natural force, which is equal to this. And since the force that we solved for earlier is greater than this one, with the kinetic friction, it means that it will slide. So then we use this whole time we're using our static friction. Sorry, that's my apologies. This problem we use our kinetic friction, because we know sliding, so it's a motion. So this right here is sliding. We figure out the force once it's sliding with the kinetic friction. We get 1 pound. We get the sum of forces in the g direction, at point G, sorry. And there it wants us to find the angular acceleration. So we get all the values, this sum of moments at G, and this is what we get right here, 2.88. And to find the acceleration at G, we just take the sum of forces in the x direction, which is equal to m mass times acceleration. Plug in the values that we do know, we get 3.22 feet over second squared. And then for problem 8, we're given this 2 uniform discs, and it wants us to figure out the acceleration of the center of each disc, and also the horizontal component of the force exerted on the disc D by the pin B. So this is disc A, our free body diagram, which is equal to this right here, which we've been doing for every single problem. Get the sum of forces at point E. E is the very bottom of the disc. this is what we do right here. And then while simplifying it, we get this right here, the equation. Disk B is basically the same thing. The only difference is that instead of C, we have the D reaction, but going in the opposite way. And that's basically it. So since it's kind of similar in that way, oh, and it also doesn't have this right here, this moment reaction. So since it doesn't have that, so I just basically simplify it to this section of from this K. The only thing is replacing this by D, which I did right here. And this, how I label this is my equation 1. This is my equation 2, since we're going to use it later. And then we look at rod CD. We look at the free body diagram, which is equal to mass of the rod times the acceleration of the rod. And then we know the acceleration of the rod will be equal to the acceleration A plus the acceleration of C. Positive acceleration, negative acceleration, we end up getting 0.08 times the angular acceleration for the acceleration. Oh, well, no, sorry, not negative. We know we minus the radius. And then we get the sum of forces in the x direction, and this is what the equation we end up getting. So we get C minus D, which equals 2.2 times the angular acceleration. So we could figure out what C is equal to in D by this equation. This one will give us C, which is right here, and this one will give us D, which is right here. Plug these two into this one right here to get our angular acceleration. So it plugged it in, and this is what we get for angular acceleration. Now it asks us for the acceleration on the center of each disc. We know, since it's the same size disc, we know that it will be equal to one another. So we just use the equation of radius times the angular acceleration, which the radius is 0.12. They have the same radius times the angular acceleration. This is what we get right here. And it wants us to get the force on pin D. We know what D is equal here. We just plug in the angular acceleration, and this is what we get for our force at D. And that would conclude the homework assignment.